Today I would like to talk about recent work that was carried out in the NMR team of the Sesame laboratory where I work in Nantes towards the analysis of mixtures using NMR spectroscopy, and more specifically towards reaction monitoring applications using flow NMR. So there are different aspects that I will cover, and I will also like to introduce the general concepts that are useful for the understanding and design of a gradient-based method for flow NMR in the spirit of a tutorial presentation. But first, I would like to that we remind ourselves why is it that it is interesting to look at solution mixtures of small molecules. And one reason is that they are everywhere. There are many fields in which the analyst is faced with samples that come in the form of mixtures. It is the case when considering metabolomics applications, trying to analyze biofluids or extracts. It is also the case in chemical synthesis when trying to understand the outcome of a chemical reaction. And while there are many instances in which these mixtures are at equilibrium and do not evolve in time, there are also many information of interest that can only be obtained by analyzing a sample that evolves in time, that is out of equilibrium, and that is typically the case in chemical synthesis with reaction monitoring, trying to learn about kinetics or identify intermediate species. So there is a strong incentive to analyze mixtures, be they at equilibrium or out of equilibrium. Now, how to characterize a mixture? Well, the most comprehensive description would typically be obtained by combining a separation method with some detection method, but there are also cases where it is undesirable or impossible to actually physically separate a component of the mixture, and it is much more interesting to do a direct separation-free analysis. That is possible with a number of analytical methods, including NMR spectroscopy, that has advantages such as the fact that it provides quantitative and structural information that is useful for identification. One challenge, however, with the most commonly used NMR methods to analyze mixtures, proton NMR, one-dimensional proton NMR, is the complexity of the resulting data, which can be difficult to disentangle. And so it is also highly interesting to use a number of multidimensional NMR methods that can still be used for direct analysis without physical separation of the component, but that separate the spectral information that help for further for assignment and quantification of components in mixtures. Now the situation is a bit different for a mixture that evolves in time. In that case, physical separation of the component is even more complicated. Direct analysis with 1D NMR is also made challenging by the complexity of the spectra. And in the case of 2D NMR, well, one challenge is the time that it takes to acquire a complete data set, which can be of several minutes or more, while it can take less than 1 second if necessary to acquire a 1D data set. And so this sets a limitation on the time scale that can be accessed with multidimensional NMR. And this is one of the motivation that has driven the development of an array of fast multidimensional and fast two-dimensional NMR methods that have now become rather mature and have been used for an array of applications. So there are different strategies such as non-uniform sampling of the indirect time dimension or ultrafast NMR based on spatial parallelization, accelerated coherence transfer pathway selection that can be combined with different 2D methods such as correlation spectroscopy, diffusion order spectroscopy, Laplace NMR, with a number of successful applications. I will give just 2 examples, one being the fact that ultrafast 2D NMR and ultrafast correlation spectroscopy experiments have been used to monitor organic chemical reactions and identify species that could not be identified otherwise, with a number of examples. And more recently, diffusion NMR accelerated with non-uniform sampling has also been used to test hypotheses on enhanced molecular motion in a solution. So there's now an array of fast multidimensional NMR methods that have been used for a variety of applications. Now, there's also the question of how the reaction monitoring data is actually collected. And the most usual approach to do real-time reaction monitoring to collect data while the reaction is going is to carry out the chemical reaction directly in an NMR tube. And I mean, it does provide real-time data, which is a good thing, and it can provide also decent temperature regulation, but there are all sorts of ingredients of classical chemical synthesis that are quite difficult to reproduce within an NMR spectrometer. One of them simply being sample steering, which can have consequences on the kinetics that are measured and that may be unreliable because of the lack of steering when measured directly in an NMR tube. It can also be harder to bring an external stimuli, such as light radiation, or to do something as simple as a dropwise addition of a reagent. So the reaction conditions within the NMR spectrometer do not necessarily faithfully replicate what would be done under the fume hood. And one possible approach to tackle this problem consists of using online reaction monitoring based on flow NMR. So in this approach, the reaction is carried out in a reaction flask as it would in a chemical synthesis lab. Sample can be stirred, there can be irradiation, dropwise addition, and a fraction of the sample is continuously circulated between the reaction flask and the NMR tube to provide real-time information, but of a reaction that is carried out in the experimental conditions of interest. So it has already found a number of applications in the field of catalysis. For example, there are nice examples of photocatalysis or metal catalysis. And one question that we ask ourselves is, right, while this does provide access to experimental conditions of interest, is it still compatible with the array of fasted NMR experiments that have proven so useful for reaction monitoring? And so we wanted to test and adapt and develop these methods such that they can still be applied in the case of a flowing sample for reaction monitoring. And today I would like to talk about three different methods. One of them is diffusion NMR. I will also describe the case of pure shift NMR to obtain higher resolution proton spectra, as well as ultrafast NMR based on spatial polarization. And what these methods have in common is that they all rely on the application of magnetic field gradients so that essentially different things happen in different parts of the sample. And when the sample starts to move, then it has consequences that have to be accounted for in the design of the experiments. So the underlying question that is common to all of these methods is what happens when a gradient pulse is applied to nuclear spins that are moving. And this has been well characterized in magnetic resonance for decades now, and it finds interesting applications in this case. So in the spirit of a tutorial, I will even start by reminding ourselves what does it consist of applying magnetic field gradient in NMR spectroscopy. So we usually make efforts such that the magnetic field is as homogeneous as possible over the sample volume so that we have narrow peaks in the NMR spectrum. If a magnetic field gradient is applied, then the field will instead varies linearly from one end of the sample to another, and as a consequence, the resonance frequency of the spins that are at one end of the tube is different from that of the other end. It varies linearly, and this is in fact the basis of magnetic resonance imaging, but here it will be used for different purposes. Now we can look at what happens to the nuclear spins as a function of time when a magnetic field gradient is applied. And for this, we'll look at an animation. What we're seeing here is a stack of magnetization vector for corresponding to different Z position along an NMR tube. And they are in the transverse plane because a 90-degree excitation pulse has just been applied. And now we can look at what happens when a magnetic field gradient pulse is applied, such that the precession frequencies varies as a function of position. And what one can see is that the spins start to precess at a frequency that depends on their position. And as a result, we can look at it again, a magnetization helix is formed under the effect of the gradient pulse. One important property of this helix is that it can be undone by the application of a second gradient pulse of opposite sign and identical duration. And if one applies such gradient pulse at a later time, the magnetization will precess in the opposite sense, and so the spins will return to their initial position. So this is the basis of a gradient echo. If two gradient pulses are applied with opposite areas, then the first generates magnetization helix and the second returns it to its initial state. So this is in a case where spins are not moving during the application of the gradient pulses. And this basic feature is used everywhere in NMR spectroscopy, in solution state NMR at least, and very much in methods for the analysis of mixtures of small molecules for a variety of tasks, be it coherent selection, solvent suppression, also diffusion encoding, spatial selection, as well as spatial polarization methods, spatial encoding of be it the chemical shift or the diffusion coefficient. So these gradient pulses are everywhere. Now, what happens if instead the nuclear spins are moving? In this case, we're considering that they're moving at a constant velocity along the z-axis while a z gradient is applied. And we can look at these animation that compare behavior where of the case where they're not moving and the case where they are moving. And again, the helix is formed and it is undone by the second gradient pulse. But by the time the end of the second gradient pulse has been reached, one can see that the phase of the spins in the case of non-zero velocity is changed compared to its initial value. We can play the animation again, and you can see that while on the left, in the absence of a velocity term, the spins do return exactly to their initial position. On the right, with a non-zero velocity, there is a resulting dephasing. That is due to the combined effect of flow and of the gradient pulse. So that would be okay if all the spins in the samples had the same velocity. In fact, it would also provide a way to measure the velocity by measuring the dephasing as a function of the gradient area. But the problem is that in a typical experimental situation, there is in fact a distribution of velocities. For example, for the flow cell that we're using for online reaction monitoring, there is a laminar flow. So there is a velocity profile with low velocity at the edges and much higher velocity at the center of the tube. And this distribution of velocity results in a distribution of phases at the end of the gradient echo. And so it's not just now a dephasing, but a distribution of phases that will result in an attenuation of the signal. So basically, one effect is that if gradient pulses are applied on pulses that are moving, then it can result in an attenuation of the signal. And it can get even worse because depending on the pump that one is using to flow the sample across the flow cell, there can, in addition, be pulsation, the flow rate that is not stable as a function of time, and these changes in velocity result in a change of degree of attenuation, and so overall it results in experiments that are not repeatable over time. And so these are the obstacles that one has to deal with when using gradient-based experiments on a flowing sample, and it has been characterized for many years and applied in different contexts, one of them being magnetic resonance imaging. And there are well-known solutions to compensate for these effects. One of them is to modify the gradient waveform such that not just the effect of the gradient alone is refocused by the end of the waveform, but also the additional effect due to velocity. We can look at the animation again. Now you can see that the initial waveform that led to a gradient echo has been duplicated with opposite sign. And if we look at the total trajectory, you can see that while at the midpoint, there is the dephasing that we saw before, at the end of the total waveform, the spins have returned to their initial orientation, even in the case of a non-zero velocity. So one can adapt the gradient waveform such that the effects of velocity are compensated. This can actually be generalized to acceleration if necessary with a more complicated waveform, but at least the case of velocity compensation is reasonably straightforward. It has been put to good use in many cases in NMR spectroscopy as well as in magnetic resonance imaging. And such compensation approach will work also for distribution of velocities, provided that it is sufficiently stable, that it is stable over the duration of the gradient waveform. So in the case of our flow cell with its laminar flow profile, there is some hope that one can compensate for the effect of the flow using such compensated gradient waveform. So now we can consider the three different cases that I have mentioned in the introduction, and starting with the case of diffusion NMR. And I will in fact talk today about DOSI, diffusion ordered spectroscopy, which is one way to analyze diffusion NMR data. So in diffusion NMR and in DOSI, one is trying to measure for each peak in the NMR spectrum the diffusion coefficient that is associated with that peak. And in favorable cases, then that makes it possible to separate the spectra of the different components in the mixture without actual physical separation of these components, because all of the peaks for a given compound will align at the value of the diffusion coefficient for that compound. That requires sufficient spectral resolution and sufficient diffusion resolution, but you can achieve virtual separation of the component of a mixture. This is illustrated here with a simple mixture of small molecules, and these results are typically displayed as a contour plot like any other 2D experiment, where we can see here the different lines corresponding to the different compounds in this mixture. So this is typically applied on samples that are in an NMR tube. And can we apply it to the case of a flowing sample? So first, let's look at how diffusion encoding works in such pulse sequences. Looking here at an animation that is designed for the case of a spin echo, but that would also be largely applicable to the case of a stimulated echo that is more commonly used experimentally. So now we're going to look again at the magnetization vector that will dephase due to the first gradient pulse and rephase due to the second one. But in the meantime, during the delay between these two gradient pulses, the magnetization vectors will now move due to translational diffusion of the molecules. So they will undergo some random Brownian motion, and their position at the start of the refocusing gradient pulse will be slightly different from that at the end of the first pulse. Let's look at the animation. We see that a helix is created, and now you can see that the magnetization vector is moving slightly, such that when the second pulse is applied, there isn't perfect rephasing of magnetization, and there is again an attenuation. But it's very different from the previous one. Here it's due to the incoherent motion of the molecules due to translational diffusion. And this attenuation is actually what we want to measure in diffusion NMR, and in DOSI, the way in which it's done experimentally is by running They spell sequence a number of times for different values of the gradient amplitude, which provide a decay curve that can be fitted with the Stage-Galtner equation to recover the diffusion coefficient for each peak, given that the different delays and amplitudes are known experimentally, are under the experimentalist control. So in diffusion NMR or DOSI, one will run a series of such diffusion-weighted spectra and fit the resulting data to recover the diffusion coefficient. Now, let's consider the case of a sample that is now flowing. Well, there's a bit of a challenge if one considers the corresponding spatial scale, because if we take a typical diffusion delay of 100 millisecond and a diffusion coefficient of 10 times 10 to the minus 10 meters squared per second, which would not be uncommon for a small molecule, then the resulting displacement occurs over a spatial scale of a few tens of micrometers. So this is what one is trying to characterize. Now, if at the same time the sample is flowing at a flow rate of 4 milliliter per minute, which would be a typical flow rate for online reaction monitoring, then the corresponding displacement is over a spatial scale that is more than 1 order of magnitude larger. So one is trying to characterize a motion that is quite small compared to the sample flow. And the sample, one can expect that the sample flow will interfere quite badly with the diffusion measurement. And this is unsurprisingly what is observed experimentally. So here we're looking at a simple mixture of 3 small molecules. Some 3 peaks have been selected for each molecule to characterize the quality of the separation. So the question is, how well are each of the spots aligned for each of the molecule, and how narrow are they in the diffusion dimension? And if one uses the classical stimulated echo experiments on such sample in the absence of flow, then of course the separation is excellent, the spots are very narrow, and the diffusion attenuation is well described by the Stage-Galtner equation. Now, if one turns on the pump, then the results are terrible, unsurprisingly, and that's because of the interfering effect of the sample flow with the diffusion measurement. One can see that now the spots are very broad, and the data is not described at all by the model. So what can one do to try and improve this situation? So we've seen in the introduction that if there is a single velocity, then there's a global dephasing, and that's okay. Now, if there's a distribution of velocity, then that results in a signal attenuation. And one possible solution is to use double diffusion encoding. So to use 2 diffusion encoding blocks instead of 1, and that should compensate for the effect of velocity while the effect of diffusion is cumulative. That was described in the case of diffusion NMR by Jerschow and Müller in the late 90s. But there remains the question of the case of a flow that is pulsatile, that is not stable over time, and that may lead to residual error. So we tried experimentally simply with our experimental flow cell and the sample flowing at 3 milliliter per minute to use double diffusion encoding. And while it did improve the situation, we still had overestimated diffusion coefficients, broad diffusion spots, as well as data that is not suitably described by the model. So it doesn't entirely solve the problem only using double diffusion encoding. Another possible approach is in fact to change the direction that is used to encode the diffusion information. This was, for example, shown in the case of convection by the Manchester NMR group that showed that they could have much more robust DOSI results by using a transverse gradient axis. So we are equipped in Nantes with a triple axis gradient probe. So magnetic field gradient can be applied along any direction in space. And I should say that I'm very much a strong advocate of using such probes for flow NMR experiments because they are much more flexible. And so in this case, we tried using, say, the X or the Y axis to encode the diffusion information, which should be much more robust than using the Z axis. And well, if we did that alone, then again, it's not as bad as using the Z axis, but it's clearly not perfect either. But nicely enough, if we do combine the two, if we use double diffusion encoding with a transverse axis, we can get diffusion NMR data that is essentially as good as that obtained on a static sample. So with this approach of using double diffusion encoding with a transverse axis, we can apply diffusion NMR and get dosy data that is reliable for a continuously flowing sample that is possibly very useful for a monitoring application. We just checked in this case using a model reaction that we could track both the concentration as a function of time and the diffusion coefficient. So here the diffusion coefficients are not expected to vary. So it is in fact a validation of the possibility to measure them reasonably accurately over a long period of time during the reaction while the sample is continuously flowing. And so we believe that this opens many opportunities for the use of diffusion NMR for reaction monitoring and using online monitoring by flow NMR. Now, another family of sequences that I wanted to describe today is the case of pure shift NMR. And specifically here, pure shift NMR using the Zenger-Sterk approach, which is also a form of spatial parallelization. So first, briefly, I would like to describe some of the core ideas of pure shift NMR, where the goal is to obtain 1D spectra, 1D proton spectra, but where each of the signal is a singlet rather than a multiplet to effectively enhance the resolution and mitigate the overlap problem that is very frequent for spectra from mixture. So how does that actually work? So if one considers a spectrum that is obtained for, in this case, a spin pair with the J coupling. So we have an AX system with two doublets. Then one can remove the effect of the J coupling over some period of time by the application of a selective pulse flanked with gradients on one of the spins. So say we have an AX system, we apply a frequency selective pulse on the A spin that will crush the signal of the X spin. So we have just one of the signal left, but it will also refocus the effect of the J coupling between A and X over some period of time, and that is used in pure shift sequences to obtain singlets. But in this case, it only operates for a single signal in the spectrum. And so the key idea that was introduced by Zenger and Sterk in the late 90s is to apply together with this frequency selective pulse a weak magnetic field gradient such that the pulse operates on different resonances in the spectrum depending on the position within the sample. And as a result, the entire spectrum is obtained at once with singlets for all of the signals. If I try and summarize it graphically, the one obtains the full homodecoupled spectrum in a single experiment, and in practice, the different parts of the spectrum come from different parts of the sample, where each of them contribute to a given signal depending on its offset. So that's the basic, very basic description of pure shift NMR based on Zenger-Sterk decoupling. And now, how will that work on a sample that is flowing? Again, one can reasonably worry that it will fail, because we're doing something that is position dependent on a sample where spins are moving. So it's possible that things will go wrong. And so we can have a look. And this is a sample of quinine on a 500 megahertz system. This is its usual 1D proton NMR spectrum, and this is the pure shift spectrum obtained on a sample that is not flowing. One can actually nicely see the relevance of pure shift NMR, because there are several cases here where multiplets are overlapped. They would be difficult to analyze, possibly decide how many signals there are, and in the pure shift spectrum, it becomes really clear. But again, if one turns on the pump and takes no particular precaution, then the result is terrible, and the signal is gone. But as we saw earlier, there are well-defined strategies to design gradient waveforms that compensate for the effect of spin motion, and typically for velocity effect. So this would be an uncompensated slice selective pulse, slice selective refocusing pulse. But if it is flanked by gradient pulse such as overall this gradient waveform as the compensated design that we saw in the introduction, then it should compensate for the effect of velocity during the selection process. And this was put to good use to use pure shift NMR in the case of convection, again by the Manchester NMR methodology group. It's the work of Elsa Queton and co-worker. And what we tried in collaboration with the Manchester group is to apply this same strategy in the case of a flowing sample. And indeed, if we do use a convection compensated implementation of the slice selective pulse, we can obtain a high quality pure shift spectra also for a continuously flowing sample, be it in this case at 1 milliliter per minute or 2 milliliter per minute, provided that the sign and amplitude of these gradients is chosen properly. One can recover the same quality for the spectra as that on the non-flowing sample. And it is actually quite sensitive to the choice of the amplitude of these gradient that flank the slice selective pulse. One can see here that the faster the sample is flowing, the narrower the conditions to have good quality data. But this convection compensated, this velocity compensation approach also applies to the case of, in here, a continuously flowing sample. And that also opens nice opportunities for reaction monitoring application in cases where overlap would make it difficult or impossible to integrate selected peaks for some samples. This is the work here of Margherita Bazzani, who's a postdoc in the team, and who has implemented these methods and shown that in this tosylation reaction, that one can accurately track the volume of the different peaks and have many more of them that are resolved in the pure shift case than in the proton 1D data. So also in this case, we think that that should be useful for reaction monitoring application. And as the final part of this presentation, I would like to show that one can also obtain ultrafast NMR spectra of very good quality for a continuously flowing sample. So first, let's go over the general idea of ultrafast NMR, which was introduced by Lucio Friedman in the early 2000s, and it makes it possible to accelerate quite dramatically multidimensional experiments. So in a classical multidimensional experiment, each of the sub-experiments is obtained independently by repeating the same scheme and incrementing a delay. And in ultrafast NMR, instead, the different sub-experiments are parallelized spatially, and so they are each performed in different slices of the sample, but at the same time. It's a very general principle that can be applied to essentially arbitrary 2D experiments. And so we were, as I mentioned in the introduction, it has proven useful for reaction monitoring, and we were curious to use it for online reaction monitoring on a flowing sample. And so we tried that. It was the work at the time of Corentin Jacquemot, a PhD student in the team. And this is a COSY spectrum obtained in less than 1 second. It's always striking to realize that this data can be obtained so fast and in a single scan, and it on a sample that is flowing at 2.5 milliliter per minute. It actually looks rather good. I was surprised and was expecting that the situation would be much worse. Now the problem started to come when we tried to integrate the peak volumes in this spectrum and track them as a function of time, which is what you would do to, say, characterize the kinetics of a reaction. And in that case, one can see here that there are strong oscillations in the data that have nothing to do with the chemical kinetics and that are due to interferences between the spatial encoding process and the sample flow. So how can we deal with this? First, to better understand its origin, we can go over the general principle of ultrafast 2D NMR and how that sequence works. So consider a system with 2 different resonances, and we will go through the pulse sequence. So there's first the excitation pulse, and we can look at the magnetization as a function of position for the 2 different resonances. And they will then go through the spatial encoding block, which overall is designed such that different positions have different effective evolution time. And as a result, the magnetization forms a helix with the pitch of the helix that is a function of the offset. So the chemical shift information has been encoded spatially. That information is decoded during acquisition with a readout gradient that results in the formation of echoes, the position of which is proportional to the chemical shift. So the indirect chemical shift dimension is obtained by the application of a readout gradient. Because this process is reversible, it can be done and undone numerous times. Meanwhile, the NMR interactions modulate the signal in the direct dimension such that when the Fourier transform gives the 2D spectrum. So, and now one can include a mixing scheme to obtain actually also correlation information. So this principle is very general, and as we can see, it relies on the possibility to form helices that encode the chemical shift information. But again, in the case of a flowing sample, there will be interferences between the process of forming and reading these helices and the displacement. One can expect, again, that there can be dephasing in the case of a single velocity and in fact also some extent of attenuation. The situation will be made worse by the distribution of velocity and even worse by the pulsation of the flow. And well, unfortunately, so far we have been, or maybe rather I have been, unable to come up with an encoding strategy that would actually efficiently compensate for these effects. Interestingly, it does work very nicely in the case of spatially encoded diffusion NMR. So ultrafast diffusion NMR works well and can be compensated for the effect of velocity with the same strategies before, duplicating the encoding scheme and changing the sign of the coherence transfer pathway. That works fine. But in the case of spatial encoding of the chemical shift, somehow that doesn't work, or it kills the information of interest as well. So there's a challenge here that I'm hoping still to address eventually. So we need to do something else. And again, you can see here experimental data where the spectra, they look good, but they're the volume of the peak as a function of time is not repeatable, so they are essentially useless. And these, they are obtained with spatial parallelization along the z-axis, because this is what we would normally do. That is what provides the highest resolution in the indirect time dimension. But in this case, we found that simply moving the encoding axis to a transverse axis, be it the x or y or any combination of them, actually does resolve this interference problem, that we now have peak volumes as a function of time that are much more stable, and we also have much less of the attenuation effect that we saw before. So I will not expand much more today. I mean, one can note that the resolution has now become rather bad, but there are solutions to this, such as using interleaved scans that we have also explored for flowing samples, and that work well. But overall, what it means is that one can also use ultrafast NMR for reaction monitoring on a continuously flowing sample. So overall, one can see that the different strategies that were developed for reaction monitoring, be it to obtain correlation information or to separate signals from different components to increase the resolution, they can be translated in the context of flow NMR analysis. And we think that this will turn out to be useful for reaction monitoring applications. And to conclude, I would like to thank everyone who contributed to this work, members of the team in Nantes. So I mentioned that the pure shift work was done mainly by Margherita Bazzoni, with support also from Armand Rejas. The diffusion NMR work was mostly done by Achille Marchand, and the ultrafast NMR work was started at ICSN with François Giraud by Corentin Jacquemot, who then moved to Sésame. This is all a collaboration with Patrick Giraudot, also from the Nantes NMR team, and our colleague François-Xavier Felpin in organic chemical synthesis. And for the pure shift work, we've been heavily collaborating with the Manchester NMR methodology group, who had developed the concept in the convection context. I would also like to thank funders for supporting this work, as well as you for your attention, and I'll be happy to answer questions you may have. Thank you.
Thank you, Jean-Nicolas, for the excellent talk. I will let people type their questions in the Q&A section. But just maybe I can ask my question first. So, what kind of gradients do you need? So you mentioned the gradients on your probe, but do you also use the gradient in the magnet itself?
So all of the experiments that I have shown here, they were implemented with a commercial, classical, high-resolution NMR probe, equipped with strip and axis gradients. So the maximum gradient that it can deliver is, I believe it's 65 Gauss per centimeter along the z-axis and 50 along the two others, and that's more than enough for what we're trying to do.
Okay, so if you imagine you want to transpose this method with benchtop instrumentation, it's not enough to use the gradients of a benchtop system.
So I mean, it's a good question, and I should say, in part because we do have benchtop NMR instruments, and some of these methods will certainly be relevant in a benchtop NMR situation. But the ones that we have are also equipped with the gradient coil, so you might as well use that gradient coil. So we haven't tried to implement this on a benchtop NMR system that would not be equipped with a gradient coil. It does raise interesting questions on the orientation of the gradient pulse, which is different on a benchtop NMR system for different manufacturers, and this must have consequences for flow NMR experiments.
Okay, thank you. Oh, so we have three questions. So the first one is, to what extent do gradient shapes affect your results? Are all shapes just as well?
So it depends. For many applications, we don't see a very significant difference. I mean, we tend to use trapezoidal shapes for in most cases, and because of the constraint on the pulse sequence instruction. For the diffusion NMR experiments in flow, we had to revert to sinusoidal shape, so they are slightly less efficient, but the experiment would still perform nicely. Perhaps the most sensitive choice is that of the gradient shape for the acquisition part of UF2D NMR. This one should rather be trapezoidal and well controlled, but it's not very sensitive, I would say.
We have another question regarding the Ultrafast 2D. So the question is, could you please detail the theoretical difficulty, the limit designing gradient schemes for Ultrafast 2D?
I'm not sure I entirely get the question. Maybe it's related to this question mark that I have set that says that I failed to achieve velocity compensation with ultrafast NMR. It's just somehow, let's put it that way. The key of ultrafast NMR, or at least as I understand it, is that the spin phase at the end of spatial encoding will have a contribution that is bilinear in the chemical shift offset and the position. And if one then tries to run and one has to preserve that contribution because that's what the entire experiment relies on. And if one does the calculation for a sample that is moving and tries to eliminate all of the V term, then somehow, for, as I understand it, symmetry reasons, that term of interest that one is trying to design is also suppressed. And yes, that's what I'm facing, but hopefully I'm wrong.
Okay. So another question regarding the reaction monitoring by DOSI. So in reaction monitoring by diffusion NMR, have you tested the effects of mass difference between the reactants and the products? I assume if the difference is not large enough, can you still do it?
So, I mean, the way the question is asked, indeed, I mean, if the difference is not large enough, then it's not large enough, and then it's not separated. And it's a really good question of how significant does that difference have to be. It's something that has been characterized quite thoroughly, starting with the work of Stilbs, and of course with the work of the Manchester NMR methodology group. And it very much depends on, are the peaks fully resolved, and are you doing univariate analysis or multivariate analysis? If, I mean, in the case of well-resolved peak, sometimes a 1% difference in diffusion coefficient is enough. In the case of overlapped peak, it's preferable to have a good 20-30% difference. Then how does that translate in terms of the mass of the compounds? Depend also on their size. So it is one of the challenges. One possibility is also to use multi-way analysis so that there are more than just the diffusion coefficient driving the separation of the spectra. These are all things that need to be explored.
Okay. Ram is asking the question, if I have a laminar flow in the presence of static spins, is it possible to take out the effect of the static spins in the flow measurement 1D?
I would need a whiteboard. I'm not sure I'm going to risk answering this. I will probably I would say yes, because you can encode if you encode the velocity, if you do a velocity encoded experiment, a series of them for different values of the gradients, then in principle the transform of that is the distribution of how many spins are at each velocity. So there should be a zero term, which I guess you can separate. So I would say yes, but
To be tested. Okay. Next question is, so first, thanks for the great talk. When using X gradients, do you put the CTP gradients on X2 or Z? Do gradients on different axes interact with each other?
So thanks. That's a really good question. so usually what we do is that there's the main task that we're trying to achieve, which is some sort of spatial parallelization, it's diffusion encoding, and we try to choose the best possible axis for that, which can be Z or transverse, depending on the application. And then for coherent selection, we use an orthogonal axis. So if we do diffusion encoding along Z, we'll be doing CTP selection along X, and the reverse. Same for pure shift NMR. And this is exactly for the reason that you mentioned, that at least on a system that is homogeneous and with free diffusion, there are the tasks that are performed along the different axes are independent. So it makes everything much simpler.
The next question is, in the future, would it be possible to monitor a several-day reaction with flow NMR, or is it better to pick samples at different time points and measure them with normal NMR?
Part of the answer is also spectrometer availability and the willingness of your NMR platform to let a chemical reaction running and flowing in expensive instrumentation in the absence of someone around to look at it. I guess in principle one can do it. In practice, we do tend to focus our monitoring applications to things that fit within a few hour single day run.
Next question is, how quantitative is the pure shift method? Do you have to substrate products as a reference? Just curious, as in a Bruker webinar, they mentioned something about lack of quantitative feature.
Again, very good question. Thanks a lot. I guess, I mean, one has to be clear on what does one mean by quantitative. So one of the key advantages of 1D NMR is that you can do absolute quantification in the absence of a standards, which I suspect is what you are referring to as quantitative. And pure shift NMR in general is not quantitative in that sense. But you still, so you still have a linear response. You can do relative quantification, and you can calibrate in a number of ways. But you have a linear response with a coefficient that is compound dependent and peak dependent for a given compound. So yeah, you can do relative quantification, and you need calibration for absolute quantification in general.
We have a question from Andrew Ho. In some flow NMR systems, the flow is bidirectional, with the capillary delivering reagents into the tube. Do you expect the same improvements with the double encoding transverse gradient pulses when the flow is in two directions?
I would say yes. So in fact, I think I didn't even mention it, but we're working with a commercial Insight MR system by Bruker that has such bidirectional flow. There's the capillary going to the bottom of the tube, and then the sample going up. So I suspect that for most of the experiments that we do, the part of the sample that is within the capillary and that is flowing down is essentially invisible, not only because it has a much smaller volume, but also because and it probably has inflow and outflow effect that are much stronger, and the gradient effect that are also stronger. But all of these ideas apply irrespective of whether the spins are going up or down or both at the same time. In fact, many of these ideas originate from convection compensation, where there's the distribution of velocity sums to zero overall.
Mm-hmm. So let's say you stop the flow and you have a back pressure, you can compensate with gradients.
So that's another strategy, to use an interrupted flow approach, provided that you can stabilize fast enough.
Yes.
So I mean, it is probably robust to some extent. On the other hand, it does provide fewer time points than a continuous flow acquisition, mm-hmm. and one also has to check that. I mean, I suspect that many of these velocity compensation methods, even in the case of interrupted flow, are still relevant, if not compulsory, because there might be residual motion within the tube anyway.
Okay. Okay, another question. Great talk. To what extent does heating during the reaction affect dosy with the flow methods? Is the double echo sufficient?
So I would not expect that the double diffusion encoding compensates for the. I mean, it would compensate the effect of motion due to heating to some extent, but there would be changes in the value of the diffusion coefficient, which would interfere with what he's trying to achieve. So yeah, it is a problem, and I don't think it's solved by the double echo method, I believe. Thank
And
you.
I will end up with this last question, but I think you already answered partially. Can we integrate a static reference in the cell for quantification?
So I think one can. It's not something we're doing in Nantes, but there are a number of examples in the literature. I think of the Toronto group of Simpson and Andre Simpson using an internal cell for the log signal, and maybe they also have a reference in there already. But one could do that.